Bismillahirrahmanirrahim. Assalamualaikum and a very good morning.
Okay, as discussed in the previous video, we have looked at the T-junction and also the resistive power divider. However, both of the designs suffer from the disadvantage or limitation on the matching, as the T-junction all ports cannot be matched simultaneously, while it has been improved by using resistive power divider. But there's another problem with resistive power divider in which the isolation is not that good. Therefore, a Wilkinson power divider has been introduced in order to improve further in terms of matching and also the isolation. Okay, this is how the Wilkinson power divider looks like. Okay, the figures show the layout and the equivalent circuit for the Wilkinson power divider. So there's a 2 lambda O4 transmission line or transformer is introduced between the port 1, the first transmission line or the input transmission line, to the output port 2 and port 3. So this is port 3 and also port 2. So there's additional of lambda over 2 elements being included in parallel to the T-junction design. So each of these lambda over transformer having the impedance of Z2 of Z0. Okay, if you still remember that in transformer design, lambda over transformer design, okay, when you have, this is the lambda over 4, so the characteristic impedance of the transformer is equal to Z1 equal to Z in Z0 square root. So this is Z in and also Z0. Okay, so in this case, the characteristic impedance for the first transmission line here is equal to Z0 as the input characteristic impedance, multiplied by 2 Z0 is the load impedance. So 2 Z0 square root. So this is equal to Z2 Z0. Okay, so and each of this transformer is connected to another resistor with the value of 2 Z0. Okay, the function of this resistor is to dissipate the power, the reflected power appears at port 2 and port 3. Okay, and also it provides better isolation between port 2 and port 3. Okay, for the two transformers, it helps to improve the matching, impedance matching between the input port and the output ports. Okay, for a matched two-way power divider or Wilkinson power divider, if you have equivalent input being divided into port 2 and port 3, and it is equivalent in amplitude also in phase, so it is a matched power divider. On the other hand, if you have equivalent amplitude and in phase signals fed to port 2 and port 3, and the output appears at port 1, so the power divider, the design is actually representing a power combiner. Okay, while a resistor, this resistor that connecting the two ports, port 2 and port 3, basically improve the impedance matching and also provides better isolation between the two ports. And the S parameter or the scattering metric for the Wilkinson power divider is given as follows. So in this case, it is a 3-port networks. So your S11 for match condition, so S11 equal to S22 equal to S33 equal to 0. And as the system provides better perfect isolation, in which the port 2 is completely isolated from port 3 and the other way around. So the S23 and also the S32 equal to 0. Okay, and the rest S12, S21, S12, S13, S21, and so on are equal to negative t divided by cert2. Okay, and these values, the parameter, we can get the parameter for S12, S13, S21, etc. by using even and odd mode analysis that I'll show all of you in the next slide. Right, in theory, typical bandwidth for Wilkinson power divider is 1.44 to 1, and for the SWR, VSWR is between 1.22 and also the isolation of 20 dB. Okay, the even and odd mode analysis is used to analyze the S parameter for the Wilkinson power divider, in which the input port can be represented by equivalent circuit. So the system is added by 2 lambda over 4 transformers, with each of these having the impedance set to Z0 to get it matched to the input and output ports, and the resistor are having the value of 2Z0 to get the system match and provide better isolation. All right, so the equivalent circuit for this Wilkinson power divider is shown on the right hand side, in which the superposition technique is used so that the circuit can be seen as symmetrical in the x-axis, as shown by the blue dash line. All right, so in the even mode, so we are assuming that the port 2 and port 3 being excited by a voltage of Vs. So for even mode, both source of Vs, positive Vs. So when the both polarity are the same, so that there's no potential difference in between these two ports, therefore the line here appears as open circuit. Same goes to this point. Okay, for odd mode, so the polarity of the port 2 and port 3 is different. So here, for example, is positive Vs, and the bottom one is negative Vs. So there's a potential difference. So the connection in the middle appears as a short circuit. Okay, short circuit. So then the system will be analyzed further to get the Z in at port 2, port 3, and etc. until you get the complete S parameter. So the total derivation, or the complete derivation for the even and odd mode, is shown in here. So you can just read through or follow the processes involved in order to get the complete S matrix or S parameter for the Wilkinson power divider. Okay, in summary, as mentioned earlier, for a Wilkinson power divider, so the scattering metric based on the even and odd analysis, you get that when the system is matched, so S11 equal to S22 equal to S33 equal to 0, and as the isolation is better isolation between port 2 and port 3, therefore S32 and S23 equal to 0. Okay, and then the input power from port 1 is split equally between two ports, in which the K squared equal to 1. This provides the power division ratio between the two ports, port 3 and port 2. Okay, if you convert this into polar the value is around 0.707, or it is equal to negative 3 dB, the 3 dB power divider, in which the power from the input port being divided equally to the two output ports, port 2 and port 3. Okay, as in the earlier slides, we have seen that the Wilkinson power divider acts as equal power divider, in which the input port, the power at the input port will be splitted to equally into port 2 and port 3. However, Wilkinson power divider can also be used for unequal splits of power, so in which the input power from port 1 will be split into two output ports with the ratio of k squared, in which if it is unequal splits, so the k2 squared k squared is equal to the ratio between p3 to p2 is not equal to 1. If it is equal split, so p3 divided by p2 equal to 1. Okay, so all transmission line sections in the divider are lambda over 4 in length, and the characteristic impedance of the line section Z2 and Z3 can be calculated by using the following equation, and the resistor that connecting between the port 2 and port 3 can also be calculated by using this equation, in which is dependent on the K. The K is the power division ratio. Okay, in summary, for Wilkinson power divider, for the S matrix, if the system is matched, so the S11 equal to S22 equal to S33 will be 0. And in the case of the normalized impedance, Zin at port 1 equal to 1, so because Zin here, it is equal to Z0 divided by Z0 equal to 1. So in terms of the forward and reverse transmission, so S12 and S21 is equal to negative J divided by Z2, or it is equal to 0.707, and S13 and S31 also same value. And for short and open circuit with ISO and perfect isolation, S23 and S32 equal to 0. Here this figure shows a design of hybrid wideband Wilkinson power divider operated in between 90 megahertz to 270 megahertz, and it is hybrid because it can be used as the power divider or power combiner. So in which you can see here there's a resistor which connected at the two ports, okay, to provide matching, better matching, and also isolation. And the port having the impedance, the line impedance of 50 ohm. Let's look at an example. Design an equal split. Okay, when it is equal split, the k squared ratio equal to 1. Power divider for a 50 ohm system impedance at a frequency of f0. Okay, so by definitions, if you want to produce a match an equal split Wilkinson power divider, so we need to know the impedance of the lambda over 4 lines, and also the R value, the resistor of the lines. So for the match impedance, the Z will be equal to Z2 Z0, and the R will be equal to 2 Z0. So in this case, Z0 is given as 50 ohm. Right, so for a perfect match Wilkinson power divider, so Z0 given as 50 ohm, and then so in order to design the Wilkinson power divider, so we have two parallel transformer, lambda over 4 transformer, so in which each of the element having the impedance for each element of lambda over 4 equal to SERT2 Z0. So it is equal to SERT2 of multiplied by 50. Okay, while the R, the resistor R equal to 2Z0 equal to 2 times 50 ohm. With that, thank you.